Hello, everyone. The lecture of this week focuses on traditional synchronization problems to serve as an example of cases within the broader field of concurrency control challenges. These challenges are useful in comparing different synchronization techniques. We use semaphores for synchronization throughout our solution investigation in this week. And it follows the typical approach for presenting these solutions. The main problems we will look at are the producer-consumer problem, readers-writers problem, and dining philosophers problem. Let's start with producer-consumer problem. It's a paradigm for cooperative processes in which a producer process generates items, generates some information, that a consumer process retrieves them and consumes them. And the shared buffer actually holds produced items in between these two processes. The introduction of a buffer becomes critical in further dissecting the unique aspects of the producer-consumer problem. The buffer acts as an intermediary space for produced items. In the scope of this problem, there are two primary types of buffers, unbounded and bounded. In unbounded buffer case, there is no given limit on the size of the buffer in these scenarios. This configuration actually enables the producer to continue producing items without considering storage limitations. However, the unbounded nature raises concerns about resource management and potential memory consumption issues, of course. And in the bounded buffer, this model, on the other hand, assumes a fixed and limited size for the buffer. This configuration puts a practical limit on the number of items that the buffer can hold. When the buffer is full, producers must wait until some more space becomes available, okay? And it stays away from potential overflow situations. We don't want to overflow the buffer. And bounded buffers address resource allocation concerns and provide a more controlled environment for producer and consumer processes. So this problem modeling, producer-consumer problem, is widely applicable as illustrated by examples such as a print program producing characters for use by a printer, or an assembler producing object modules for use by a loader, okay? But the challenge is to effectively organize the interaction of these processes in order to ensure proper synchronization and avoid potential issues. Since the shared buffer holds produced items, the challenge lies in ensuring producer doesn't overflow it, and also consumer doesn't consume from an empty buffer. So we see a mutually beneficial relationship between a producer process and a consumer process in the dynamics of this paradigm, okay? So the basic structure can be found in the flow of information. Producer creates data and consumer uses that data, okay? Producer activity can create data at any time. This could be result of the producer processes computations, user inputs, or any other type of information generation. And a consumer activity can accept data as needed at the same time. This need arises independently of the producer's actions, and it reflects the consumer process's demand for relevant information. And buffer acts as a mediator between these potentially asynchronous activities. Its role is to temporarily store the data produced by producer until the consumer is ready to accept and consume it. So this buffer serves a synchronization point, which allows the producer and consumer to operate independently and without direct dependency. So this dynamic interplay forms the basis for the producer-consumer dynamics, showing the simplicity of coordinated information flow in concurrent systems. The difficulty lies in efficiently orchestrating this exchange, especially when dealing with variations such as unbounded or bounded buffers, each with its own set of resource management and synchronization considerations. And let's look at the solution. Regarding the bounded buffers producer-consumer problem. The bounded buffer is strategically implemented as a circular array, okay, like this. And we use two logical pointers, in and out. These are our two logical pointers. And these pointers are critical in coordinating data movement within the buffer. The following are the key components. So the structure of a circular array is designed for the buffer structure, okay? And it provides a dynamic and continuous storage space for data generated and consumed. This circular arrangement enables easy navigation between the buffer's beginning and end, eliminating the need for constant resizing. We use two logical pointers, in and out, act as navigating guides for the buffer's content. And actually, pointer in is a dynamic pointer that indicates the next available or free position in the buffer where newly produced data can be placed. The in pointer dynamically adjusts to the next position in the circular array as data is generated by producer process. And out pointer, on the other hand, indicates the first full position in the buffer. So it shows where the consumer process should begin retrieving data. The out pointer moves to the next occupied position in the circular array as data is consumed. The shared data consists of control variables like in and out, as well as count. So this count variable is using to store how many items are currently there in the buffer. Let's begin with producer process code. So to always generate items, the producer process runs indefinitely, okay, within the while loop. It determines whether the buffer's maximum capacity has been reached, okay. If this is the case, it enters the busy wait loop, and it does nothing until an available slot in the buffer is found. When an available slot becomes available, it inserts the newly generated item to the buffer at the in location. So the in index is then circularly updated to the next place in this line. And it assures that it wraps around if it hits the end of the buffer, okay? Finally, to represent the insertion of a new item to the buffer, the shared counter, the count variable is incremented here. In the consumer process, in the consumer process, like the producer, it keeps going forever in a while loop, okay? To consume items. It determines whether the buffer is empty in this condition, okay? If this is the case, it again enters a busy wait loop and does nothing until there is anything to consume, okay? When an item is ready to be consumed, it retrieves it from the buffer at the out location and saves it in the next consumed. The out index then updated to the next place, ensuring that it wraps around if it hits the end of the buffer. Finally, the shared counter count is decremented again to signify an item being consumed from the buffer. Okay, so to make sure the solution works properly, the crucial step of increasing and decreasing the count, okay? Increasing and decreasing of the count must be carried out atomically, okay? Atomically change count. Remember from last week that an operation that finishes completely and without interruption is said to as atomic or indivisible, okay? Indivisible or atomic. In this case, the integrity of the shared counter must be preserved and race problems in a concurrent environment must be avoided by performing the counting increment and decrement operations without interrupting. So great. Now, as you guess, we need to use semaphores to ensure synchronization and to resolve potential issues related to count variable. Now let's integrate these semaphores into the producer and consumer process. So the producer and consumer processes share the following data structures. N is the maximum amount of produced information. And we use two semaphores as named as mutex and empty and full. Sorry, three semaphore. I was saying wrongly. In the modified producer process code with semaphores, we see after creating a new item, the wait empty method ensures that there's an empty slot in the buffer to add this item to buffer, okay? And wait mutex is used for mutual exclusion. And it prevents multiple processes from accessing the buffer at the same time. We only want one process to be in the critical section. And the item is then inserted into the buffer by the producer, and the in index and also counter variable are updated within this section. At the end, it communicates that producer critical section code is completed, okay, and that the number of consumable items has increased. So after updating the buffer, okay. In the modified consumer process code, we now first use the waitful method. And this operations ensures that the buffer has at least one item to consume. And in the wait mutex, we want to ensure mutual exclusion and preventing multiple processes from accessing the buffer at the same time. Then the consumer reads the item from the buffer and updates the index out inside the critical section, okay? And it first signals for critical section availability and signal mutex, and then the number of consumable items has decreased after updating the buffer. At the end, by incorporating semaphores, we introduce synchronization mechanisms to prevent race conditions and ensure proper coordination of producer and consumer activities in the bounded buffer scenario.